Everyone, welcome to Last Minute Maths again. In this video, it's actually going to be a bit of chemistry. All right, we're going to cover some GCSE chemistry material dealing with covalent bonding. All right, I'm going to jump straight into it. If any of you find any questions, any clarification you want, please do leave it in the comments, and then I'll come back and give you any explanations you need. All right, what is covalent bonding? All right, it's bonding between atoms of non-metals. So it's non-metal to non-metal. All right, and I'll go back to my colors. So important, non-metal to non-metal only. Remember that non-metals always want to gain electrons. All right, short form E minus electrons. Okay, because they both want to gain, right? You can't have electrons being moved from one place to another, etc. So what they do, they end up sharing electrons, all right? And the way they do it, if we take an example of hydrogen and fluorine, okay, we know that hydrogen outside its nucleus has only one electron. All right, you can see that there. In the fluorine atom, you've got two in the inner ring. All right, so that one there, and 7, okay, around the outer shell altogether. Remember that atoms want a full outer ring, okay? Atoms want a full outer ring. In most cases, that means 8, all right? 8 electrons, except hydrogen, okay? Hydrogen wants 2. And so all the others, as far as GCSE is concerned, will want 8 in the outer ring, whether it's by gaining an extra electron or 2 to complete the shell, or by getting rid of extra electrons in the shell to drop down to the lower one, right? Whichever the case is. So the way they do it is they actually get together and they share the outer shell electrons. So hydrogen gives the fluorine access to its outer shell electron, and hydrogen gets access to the fluorine outer shell unbonded electron, the single electron. As a result, the two atoms each then get their full outer shell and they're happy, all right? So that's like a completed bond. And this, as many of you will already know, is called a dot and cross diagrams. Okay, in a dot and cross diagram, you only need to show outer shells. There we go. Right, so the properties of this, basically, hydrogen and fluorine get together and they're sort of like unbonded electrons, they share, and they both get the benefit of full outer shells, all right? So, as I said, each atom achieves a complete outer shell, and the molecule remains neutral, all right? Because you're not actually transferring or changing the number of electrons in total, all right? Neutral atoms come together and make a neutral molecule. Now, that is actually fundamentally important, all right? Because there's no overall charge, there is no electrostatic attraction between molecules. Okay, and as a result, there are very weak or effectively zero forces between molecules, right? And that effectively creates the situation where the molecules are not attracted to each other, as we've said, and so they have very low melting boiling points, all right? I'm going to come back to the diagram for a moment. So effectively, each molecule like that is independent of the next. They don't interact really with each other. They're all whizzing around and there's nothing pulling them together. All right. So no forces really. Okay. And these are called simple molecules, where they are independent of each other. All right. And so, very important point about simple covalent substances is that they have low melting and boiling points. As a result, they are usually gases at room temperature, sometimes liquid. Room temperature and pressure, that's RTP. Room temperature, pressure. Okay. And they do not conduct electricity. All right. Because there are no charged particles. To flow around, if you want to move it that way, to move or flow. Okay. The other important thing to note is that the actual covalent bond between the atoms within the molecule, right? Very important to work that out. Within the molecule are very strong. Right? The electrons are held tightly. Okay. Electrons held tightly between the nuclei. And cannot move. Hence, they don't conduct any electricity. All right. Okay. Special cases of giant covalent lattices, right, where they're not simple molecules but giant covalent lattices. All right. A couple of examples, which I'm sure you're familiar with: diamond and graphite. Okay. This is how they look. With diamond, you've got each carbon atom, all right, bonded in what's called a tetrahedral structure to four others. So 1, 2, 3, and 4. Okay. And this is three-dimensional. Now, as it's three-dimensional, that means it can withstand forces from all directions. Okay, makes it very, very strong. It's a very strong structure. And because each carbon is fully bonded, in other words, carbon can make a maximum of 4 bonds, and that's exactly what it does in diamond. There are no spare electrons. Now, if I compare that to graphite, each layer, right, graphite comes in layers. Each graphite layer has like carbons with 3 bonds in them. Now, which one's the best one to show you with? Let's take that one there. All right. So that is bonded to 1, 2, and 3. Okay. Each carbon is bonded to 3 others. That means there is 1 extra electron in each carbon which is not bonded. All right. And I'm going to put that in the thing here. Okay. And so there are, between layers, electrons between layers, and these can conduct electricity, which is why graphite is often used for the electrodes in electrolysis. All right. So you've got hexagonal structure, and each layer is called a sheet of graphene, right? So graphite is made up of layers, multiple layers of graphene, okay? And they're in one plane and they're hexagonal, right? So form little hexagons. To summarize exactly what those properties are then, all right? So with diamond, you've got a 3D structure, extremely hard material, probably the hardest material in nature, okay, that is used for many, many different things like cutting glass, grinding even metal, all right? Very high melting point, much higher than even some metals. Does not conduct electricity for what we've just said before, that all the electrons are actually engaged in bonding, so there are no free electrons, all right? And each carbon bonded to 4 others. Okay, so those are the main properties of diamond. We all know diamond is usually transparent but can have colors. Graphite, on the other hand, is made up of 2-dimensional layers, right? As we already talked about, so flat layers and multiple layers then make up some sort of a 3-dimensional shape, if you like. The material is generally soft because it has no strength in the 3rd dimension, if you like. Yeah, very, very weak bonding between the layers. And remember, the layers are actually slippery. Okay, they can slide over one another, and that's why it's used in pencil lead. All right, pencil lead, what you write with, is actually made up of graphite. So it's layers of graphene that you're putting on the paper every time you use a pencil. What we talked about in the diagram earlier, because each carbon has that spare electron which it releases between the layers, so call that delocalized electrons. That's what excuse me, that's what allows it to carry a current through it, yeah, conducts electricity. It also can conduct heat very well, all right? The structure is not so rigid that it can't vibrate, so it can conduct heat, and it has a lower melting boiling point than diamond. Let's cover that. And remember, each carbon is bonded to 3 others, all right, as opposed to diamond was bonded to 4. So those are the main properties of diamond and graphite. You need to be in your exam able to discuss those properties and explain them in terms of their differences in bondings and structure. Okay, so pay particular attention to this group that I've just gone through here, these discussions. The last one that you need to know for the GCSE papers are the fullerenes. All right, fullerenes are effectively, like in this diagram here, hollow spheres, okay, made of graphene-like layer. The difference between this and graphene as a sheet is that in the middle, if you can see, there you've got a hexagon, all right? And next to it, you've got a pentagon, all right? Whoops, bad handwriting. Pent and hex, all right? So that's the difference between the structure of this and between that and the one for graphene. Okay, so it's a graphene-like layer. So imagine you take a piece of paper and somehow you find a way of folding it into a sphere. So it's hollow inside, and the outer layer is made up of this sheet of carbon atoms bonded with some of them hexagons, some of them pentagons. So some of them are actually bonded in a different structure, but each of them to three others. All right, that's the standard. Okay, again, because they're bonded to 3, there are spare electrons, okay? And so can conduct electricity very well, all right? So make a note of that. And the closeness, the way the carbon atoms are, they actually can act as a barrier, all right? And it's interesting to note that nothing bigger than a hydrogen atom can pass through. So, for example, if you try to put helium gas through it, it can't pass through it, can't enter the hollow space inside. All right. Fullerene, and I suppose I ought to explain one thing here. The most common one that you see, the first one is C60. So it's one sphere made up of 60 carbon atoms. And they go up. I mean, there's more like C540, C720, I think there is, yeah, etc. So there's huge, huge molecules that can be made in this way. The smallest one, the one that's actually used, or they're trying to use, is a C60, all right? Buckminster Fullerene. Okay, I suppose I'll put that in there. Okay, that's in your textbook, so if not sure, either ask me in the comments or look it up in the textbook by all means. All right, one of the really special properties of fullerenes is they're very, very tough, but light, very light, yeah? So in some ways, it's almost like the perfect material, very strong, but extremely light. And it's also the thinnest material, right, known to man at the moment, because it's just one layer of atoms, okay? And the important part of that, this very tough bit, it's actually been proven to be 200 times stronger than steel, weight for weight, okay? So people are looking for many more uses for this. Some of the uses that have already been thought of and implemented, it's medicine is one, where you can actually put specific, medical molecules or drugs molecules inside the sphere and have it delivered specifically to where it's needed in the body. All right. So medical uses, it can be used in batteries, solar cells, because of their excellent conductivity, all right, and because of the strength, they can be used to strengthen polymers, so plastics, carbon fiber, that sort of thing. So start replacing metals and other resource-intensive materials, all right? So that's everything you need about covalent bonding, okay? The important facts are there. The application questions often come up with things about fullerenes, or indeed, a typical question is about the differences between diamond and graphite, and indeed why they are so different from simple covalent molecules. All right, so please do go through that. If there's any questions, as always, leave it in the comments, and I'll be very happy to respond to that. And do watch out, there'll be other videos, both science and maths, over the next few days as the GCSE season starts. So do watch out for that. Thanks for watching. And if you are preparing for your exams, good luck.